Okay, well, maybe we should make a start. So thanks everyone for coming. I guess this is our first talk for UPAC for the year, and we've got Lucas talking about on Bogomolny equations and Cauchy problems.
Thank you very much. I would like to thank to G Woods for making possible for me to deliver this talk. Thank you very much, Jess. And okay, so the goals of this talk are several. Mm, Namely, we would to derive Bogomolny equations for the restricted Baby-Skirma model in two dimensions using so-called strong necessary conditions method. And the two-dimensional Heisenberg model of ferromagnet, especially we would like to solve exactly Cauchy problem for these equations. So this was an answer. This is an answer to Bolesław Szafirski's question, whether one can formulate and solve the Cauchy problem associated to Bogomolny equations derived using strong necessary conditions method. And we do not assume anything about the form of a potential V of a restricted Baby-Skirma model. The results presented here were published in this paper. Okay. Okay. So maybe some introduction. Uh, as this is often a very well-known fact from science, some big discoveries uh, are made by people simultaneously and independently. And this very interesting story that Bogomolny equations were derived not by Bogomolny historically, but about 1 year before him by Balavin, Polyakov, Schwarz, and Tubkin for, as I remember, young Mies theory. But this so happens that these equations are more known as Bogomolny equations. Okay, so let's take into account the following Euler-Lagrange equations for model Phi24. We have spontaneously broken symmetry. Of course, we can define topological charge given by the boundary values of field phi. And of course, we can see that these Euler-Lagrange equations are generated by energy functional. And this is just the Bogomolny trick that we can write down this energy functional in such a way that the first part is given by this integral, and the second part is integrated, and this is value of a topological charge. And what is the reason of such operation? The reason is such that we would like to derive Bogomolny equations for this model, and owing to the equation number one, if we require reaching the minimum by the functional, the first term must vanish. So if this term is vanished under the square, then this term is just the left side of Bogomolny equations, and sometimes these equations are called as BPS equations. And Bogomolny equations for this model have the following form, and of course the well-known solutions of such equation is the so-called king. Then of course the functional attains the minimum. So this version of operations leading to obtaining Bogomolny equations is called as completing to square. However, there are some other methods of deriving Bogomolny equations. Just strong necessary conditions method, which I would like to analyze in this talk. This method was introduced by Krzysztof Sokalski in 1979 and developed by him and his collaborators. And I was one of these collaborators. Unfortunately, three of these people died several years ago. And first order formalism, this is the other method developed by other people, on-shell method, BPS Lagrangian method, and the so-called first order Euler-Lagrange formalism, which can be considered as a development of the strong necessary conditions method. Okay, in further part of this talk, I would like to focus on deriving Bogomolny equations using SNCM, strong necessary conditions method. And the results presented here reply also to the question asked in 2001 by Professor Szafirski to Professor Sokalski, namely whether one can formulate and solve a Cauchy problem for the equations derived using strong necessary conditions method. Several remarks concerning Baby-Skirmer model. As you know, surely this model is an analogical model on plane to the Skirmer model in three-dimensional space. This model, Baby-Skirmer model, can be applied to describe quantum Hall effect. The target space of Skirmer model is SU2, and the target space of Baby-Skirmer model is S2. Magnetic skirmions are considered to be applied in spintronic devices, so very, very interesting example of applications. In these both models, Skirmer and Baby-Skirmer, static field configurations can be classified topologically using their winding numbers. Okay, we consider such energy functional for restricted Baby-Skirmer model in 2 dimensions. We neglect static sigma term. So the only terms are kinetic term and potential. We make stereographic projection, so we translate this Hamiltonian to the terms of the fields omega and omega conjugated omega. So density of energy functional of this functional after stereographic projection has the following form. Okay, extremum principle applied to the functional number 4, to density of the functional, generate Euler-Lagrange equations as follows. Yes. Okay, so the key idea of strong necessary conditions method is such that instead of Euler-Lagrange equations, we can consider strong necessary conditions. So we demand vanishing of the pieces of Euler-Lagrange equations. Yes, this derivative, and this derivative, of course, with the conjugate analogous. Yes. However, such operation is in majority of cases, this is very strong operation, and very often we can expect rather trivial solutions. So in order to get a chance for obtaining some non-trivial solutions, we make gauge transformation of a functional of a Hamiltonian. Namely, we add to the Hamiltonian such functional that local variation of this functional with respect to the field variable vanish automatically. So Euler-Lagrange equations, owing to such operation, are invariant with respect to the above gauge transformation, in contrary to the strong necessary conditions. Such gauge transformation of a functional leaves Euler-Lagrange equations invariant. However, the strong necessary conditions are not invariant. And this is our hope for obtaining some non-trivial solutions of derived equations. Okay, in the case of restricted Baby-Skirmer model, the gauge transformation is as follows. And so I key are the densities of the invariants, such invariant, and the remaining invariants are called as divergent invariants, and the functions g1, g2, g3 are at this moment unknown, and we have to determine them further. We assume, of course, that these functions are the functions differentiable and smooth, very good functions. They are of a class C2. Okay, so we have made gauge transformation of the Hamiltonian, the density of Hamiltonian, and we now apply the strong necessary conditions. We differentiate this density of the Hamiltonian after gauge transformation with respect to omega, conjugated omega, and their derivatives. Okay, so let's observe that, of course, owing to such operation, we have obtained the differential equations of order 1, first order. However, we have very, very big number of equations. We have to make this system self-consistent. Okay, so we have to reduct the number of independent equations by an appropriate choice of a function g1, g2, and g3. Second remark is such that such ansatz of such choices of the functions g1, g2, g3 exist only for some special forms of a potential v. In most cases of potentials, for many nonlinear field models, such reduction is impossible. So we will not obtain, in such case, Bogomolny equations. However, we can try to solve such equations obtained by applying strong necessary conditions method. In this case, it turns out that deriving of Bogomolny equation is successful. So we have to eliminate in the equations 8, 9, 10, 11, 12. Okay, we have to eliminate in the equations 8 and 9 all terms, including the derivatives of the field variable, omega and omega conjugated, okay, and we obtain the equations with respect to the potential V. Okay, but however, before this, we have to choose some such forms of the functions g1, g2, and g3 that the equations 10, 11, 12, and 13 become linear dependent. So the number of these equations from 10 to 13 will be reduced to 2. Okay, and it turns out that such operation is successful. The proper choice of a function g1 is as follows, and the functions g2 and g3 have to be constant. And we obtain the condition for the potential by integrating the equations obtained from the equations 8 and 9 after eliminating the derivatives of omega and conjugated omega, and we obtain the conditions for the potential. So after inserting, I apologize you for some misleading numeration of equations. After inserting 16 and 15 into equations 10, 11, 12, and 13, we obtain one equation. Yes? So this is the candidate for Bogomolny decomposition, Bogomolny equation. And the final form of this equation is as follows. Because we replace the function g1 by with the expression of potential V using the equation number 14. And this is the Bogomolny decomposition, Bogomolny equation for restricted Baby-Skirmy model in 2 dimensions for arbitrary potential. An analogical result can be obtained also in the case of 3-dimensional BPS-Skirmy model. This is a 3-dimensional BPS-Skirmy model, and we apply exact, very similar operation. We make gauge transformation using the invariance. Yes, we add them to the Lagrangian densities of the invariance. We apply the strong necessary conditions. We derive the so-called dual equations. These dual equations are these equations following from applying strong necessary conditions. We make them self-consistent by proper choice of a functions g1, g2, g3, and g4. We have 4 functions because we have here 3-dimensional model, yes? And we get the BPS equations, where the potential V is connected to the function g1 by the following condition. For the case C2, we have Bogomolny equations for BPS-Skirmy model. For non-zero, for positive C2 constant, we have a non-Bogomolny equation, and this coincides with non-zero pressure equation for the BPS-Skirmy model. So this is rather unexpected, as I think, interesting observation that using strong necessary conditions method and the method of deriving by this method Bogomolny equations, we can obtain not only Bogomolny equations but also some its non-zero pressure generalization. Okay, and now let's come back to the Bogomolny equation obtained for restricted Baby-Skirmy model, and we have to we want to solve exactly these equations for the case of Mexican hat potential. So we want to find now an exact localized static solution with localized density of energy of a Bogomolny equation, Bogomolny decomposition. So we have hedgehog ansatz, and we solve these equations in the case when C1 is equal to 0. So we insert this ansatz into this equation, and we formulate the Cauchy problem. Yes, now the unknown function will be the function f, and we impose the condition, such condition that in point 0 we demand that this function must be constant. So in this case we put, for example, C0 equal to 2. We are interested in obtaining a localized solution, so we also impose the asymptotic conditions. Yes, we want to vanishing of function f in the infinity, and we of course demand vanishing of the density of Hamiltonian in the density. As it turns out, this problem can be solved, and after some simplification, we obtain the solution of the function for the function f. We have a Lambert function here included in the solution, and after some simplifications for such values of the constants, we get such solution, and the feature of the solution is localized solution. and density of energy is also localized. Okay? So this is also another interesting fact that the found solutions and the density of the Hamiltonian, but of the ungauged Hamiltonian are localized. But what about the gauged Hamiltonian density? It turns out that the gauged Hamiltonian density is equal to zero. So we can consider this fact as a degeneracy of the Hamiltonian. And the problem of a degenerate Hamiltonian in the case of theory of gravity was investigated, for example, by Sanyal in his paper on Del Castillo, Miron, and Rojas in 2013. This corresponds to the fact that if one considers two versions of field theoretical Lagrangian, ungauged and gauged on total derivatives of any function of field variables, then the energy momentum tensors corresponding to each of these Lagrangians will be different. Yes, the Lagrangians generate the same Euler-Lagrange equations. However, the energy momentum tensors will differs each other. So we can say that there is an impact of a gauging of the energy of a ground state of medium. Such a term can appear only in crystals not possessing the inversion center, and this causes the spiral ordering of magnetic moments. Kiselev and Batalov analyzed this issue in 2023. Okay, so we can say about breaking some symmetry, yes? The Euler-Lagrange equations are the same for the both Hamiltonians. If we say about the, for example, restricted by Beskirma model, gauged and ungauged both Hamiltonians generate the same Euler-Lagrange equation. However, on the other hand, the density of the ungauged Hamiltonian for found solutions is non-zero, and the gauged Hamiltonian has the density as zero. So the effect of vanishing of energy momentum tensor when we have appearance of topological invariance in action functional was established by Hosoya in 1978 for some two young means family models in SU2 case, also in 70s. However, this result has been obtained for a version of BPS equations derived just by using the original Bogomolny approach, namely by classical completing action functional to the square. So the forms of the invariance used there had been special. In contrary to this paper, we used generalized forms of the invariance. Yes. So the effect of the degeneracy of Hamiltonian for the restricted by Beskirma model had presented for the first time in my paper, by first time to my best knowledge. Okay, and we can also ask whether two-dimensional Heisenberg model can be analyzed by using strong necessary conditions method. And of course, we can also, for this model, derive Bogomolny equations by using the procedure which I have described several moments ago. We make gauge transformation, we apply strong necessary conditions, we obtain the system of dual equations, and we have to make the equations, the system as self-consistent. We choose the appropriate forms of the functions g. Okay, and we can obtain also the following, the analogical problem about the Cauchy problem. Yes. And okay, this answer to the question concerning Cauchy problem for such Bogomolny equations, the question we can reply to this question positively. We can solve Cauchy problem for this case. Okay, so summary to sum up. We can apply strong necessary conditions to derive Bogomolny equations, Bogomolny decomposition. This technique can be considered as an algorithm, in contrary to Bogomolny classical trick, where proper manipulation of terms in energy functional for a given phi theoretical model in many cases was impossible. And it's very hard in general to manipulate, to choose such terms in the energy functional that we obtain the energy functional generating the same Euler-Lagrange equation to a given phi theoretical model, yes, and we obtain Bogomolny equations. By strong necessary conditions can be considered as an algorithm. This method also can be applied for obtaining Backlund transformation, and this was this is connected to some results obtained by Sokalska and Lisowski and Wietecha, but this is not my branch. Uh, maybe in future. And the answer to the question asked in 2001 by Professor Szafirski to Professor Sokalski is it is possible to formulate and solve the Cauchy problem for the equations there is using strong necessary conditions method, especially for the Bogomolny equations. The answer is positive. So we can also consider applications of this method for other field theoretical models. And thank you very much for your attention. Okay.
Great, thank you. Um, I guess, does anyone have any questions?
Maybe I might start. Thank you for the talk. I was just wondering if I could clarify the strong necessary conditions method. Um, yeah, would you be able to talk through that again? Say like, what's the general algorithm? Say like with the sine-Gordon equation, so forth. Like, how would you do the strong necessary conditions for that? Because you said like you can complete the square, right? To do the
Cosine
Bogomolny
Gordon?
trick. Yeah,
Cosine Gordon, yes.
as an example, like
Yes, yes.
a
One
more
moment,
simple
please.
example.
One moment, please. One
Yeah, that's
moment,
okay.
please. Yes, 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 yes. And the reply to your question, one moment, please, uh, is essentially published by
Hmm.
Sokalski, Wietecha, and Lisowski, and I would like to show some papers because this is, of course, very important question. One moment, please. Okay, and I have found one paper, and now the second paper. Oh, okay. And maybe I share my screen.
Yeah, sure.
And yes, this was Sokalski introduced his method in 1979, and he was developing this method with Paweł Jochim in 90s, and he broken his activity in this field, and he came back to this issue of strong necessary conditions method in 1999 2000 when I was became his PhD student, yes? And this was my colleagues, unfortunately, Sokalski and Dziszewski died. And this is the first paper of them presented very wide extended strong necessary conditions method, and they focused here on deriving Rase-Backlund transformations. And as I remember, they considered a class of very wide class, very big class of nonlinear Klein-Gordon equations, and they derived Rase-Backlund transformation. However, as I remember, they also, in this paper or in the second paper, I will present that paper for a moment, they were dealt also with the sine-Gordon equations. The nonlinear Schrödinger equation, yes. The computations are sometimes rather hard. However, they are possible to do. Okay, one moment. Oh, this is the second paper, Acta Physica Polonica B, variational approach to the Backlund transformations. Aha, excuse me. So not this, but this one. Because what is the problem? If you have, for example, I would like to write something on screen because this was okay. If you have a sine-Gordon equation, this equation is considered using field variables which have real values, yes? Because u is a function of x and t. And as you remember, strong necessary conditions method demands usually making gauge transformations. So we would like to go from the original Lagrangian to the gauge Lagrangian or Hamiltonian, and we go from the original Lagrangian to the gauge Lagrangian density by adding the sum of invariants. And the first invariant is the topological invariant. However, if you have topological, however, in the case of one field variable with real values, you have a trivial topology. Because if you have two independent variables, x and t, you have the homotopy group P2S1. So in this case, the topological invariant will be as equal to 0. So what is the philosophy? There are two possible ways of applying strong necessary conditions method. For obtaining Backlund transformations, if you have such topology, trivial topology, you have not only make the gauge transformation for the given Lagrangian field of field theoretical model, but you have also complete the Lagrangian in such a way. The first Lagrangian is the functional of u. Yes, this is the original Lagrangian, for example, of the sine-Gordon equation. And you have to, in order to apply the gauge transformation, which will formulate, which is good form of, non-trivial form of invariant, topological invariant. You have to complete the Lagrangian to the analogical Lagrangian for sine-Gordon model, but using second field derivative, second field variable v. Of course, v is also a function of x and t. And you now can say about non-trivial homotopy group, and now the topological invariant is non-zero. So you make gauge transfer, you complete the set of invariants, topological invariant and the derivatives invariants. You make the gauge transformation. You apply the strong necessary conditions. We derive the dual equations. Yes. You make them self-consistent by proper choice of the function g1, g2, and g3, and you derive Backlund transformations. If this is possible, and this is possible, of course, this is possible for Sine-Gordon equations too. And they showed this in, as I remember, the first paper presented here. I have presented this paper. This is the first case. And you obtain in such a way Backlund transformation. Bogomolny decomposition demands originally the non-trivial homotopy group. This homotopy group must be originally non-trivial in a natural way. For example, as we have in Skirme model, we have the complex valued field variable omega. Yes, so we automatically have omega conjugated. We are not forced to add the other Lagrangian with the additional field variable. Yes, and you have applied the same technique, gauge transformation, strong necessary conditions, and yes, for Sine-Gordon equation, as I no, this is possible, but I have not derived Bogomolny equations for such situation. But the Sine-Gordon equation with the complex valued field variable. Yes, this should be possible. However, I was not did do this. I was not analyze the situation. So the gauge transformation is have the sense only in such case if you have two, for example, three, yes, three field variable, and this situation is in the three-dimensional BPS Kerman model, but the topology must be non-trivial. So if you have, for example, three-dimensional model, so for example, S3. S3 or S2, but in the case of S2, situation is very, very interesting, but very, very hard because the Hopf index must be considered. The Hopf index is very hard issue because the very elegant computations, very nice computations, as presented by me in this talk, for restricted baby-screamer model, they are possible owing to the fact that the densities of invariants are local functions with respect to the field variables, yes, and to their derivatives. But Hopf index, Hopf invariant, this is very unnice expression because in general its densities is non-local. And Sokalski and Joachim analyzed such situation with Hopf index in their paper in 1994, as I remember, or 1993, for Heisenberg, three-dimensional Heisenberg model, but the computations were very hard, and they focused only in simple case, and they proved that in that case the solutions can be only trivial. So I hope that my answer shed a light for your issue.
Oh yeah, thank you. It's
Yes, thank you.
yes, very good.
So
Very
thank
good.
you very much for your remark, of course.
Yes.
Thank you.
Other questions? maybe more of a general sort of question. I guess in all of these cases, we consider Euclidean signature. What happens if we try and look for like soliton solutions in some mixed signature? What's the subtlety?
Please repeat. We consider what? Because I
Euclidean signature, right?
what signature? What?
Euclidean.
Dear Jess, I have an audition defect, so I have some
Sorry.
problems with. So I apologize. We consider which model?
In any of these models, right?
Uh-huh.
Usually they're in Euclidean space.
Uh-huh.
So is there any subtlety or, if we want to switch to, say, Lorentzian signature, like a 2+1 or a 1+1 signature?
Yes, 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 yes. Aha. So you say about the case when you have dynamics, yes?
Yeah,
Uh,
yeah,
time, yes?
yeah.
Yes, yes, this is possible. And one moment, please. And I focused rather on one moment. I have such a situation. Yes, this is possible. This is possible, and you thank you very much for your question because this situation is for Landau-Lifshitz equation, and I analyzed this in my PhD thesis, but I have not published as yet. Yes, I am. I came back to to this model, Landau-Lifshitz equation. Uh, I maybe I show this. Yes, yes, one moment, please. Yes, 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 yes. Oh, yes. Landau-Lifshitz equation. So this is equation for. I apologize you, but the text is not perfectly written as yet. I'm doing it all time, and I'm hope that this will be submitted for publication next month. We have such situation. We have Heisenberg model with time. We have Hilbert damping term, and we have Landau-Lifshitz equations. So this is such situation. After stereographic projection. But however, there's some problem with making the dual equations self-consistent. And I have applied some technique for making them such self-consistent. Oh, this is a rather complicated case. So it turns out that if you apply strong necessary conditions method for this model, you have a problem with the functions G3. The function G3 is present in the second derivative invariant. And this function is non-analytic in the original approach. And I solve this problem by making some trick. However, now I of course, would not like to speak it in details. However, yes, this is possible to derive Bogomolny equations. But the work is in progress, and I hope that it will be finished in future in April.
Okay, okay, great.
Thank you,
Thanks.
thank you, many thanks for
Thanks.
your question.
Are there any other quick questions?
I have another question. Does the strong necessary conditions, do these apply to like any integrable model, or is there a certain what's the conditions in which this method applies?
Please repeat because I.
Oh, okay, yes. What conditions are needed to apply the strong necessary conditions method? Does it apply to any integrable system? Or
Yes.
yeah,
What about integrability? Yes.
yeah.
Aha. Okay. Because I'm not sure whether I have this paper here. One moment, please. Very important issue. Maybe one. Uh, no, this issue was analyzed in a paper of Sokalski and me in Sokalska, and I have this paper, but okay, maybe I. Okay, and else. Oh, I have not this paper in my computer now because I have. But you have an opportunity to get this paper. This is my first paper concerning the strong necessary conditions, published in 2002, the existence of Bogomolny decomposition by means of strong necessary conditions. And we derived the Bogomolny equations for a non-linear field equation in 2 dimensions. And what is the situation? If a potential, this is not very easy to. Okay, but maybe I. Do you see now the script? Fine. So
Yes.
you have such situation. You have a kinetic term depending on two field variables and a potential. I do not remember the exact form because this was more than 20 years ago. And now the equations were coupled. The equations were coupled. We can go to light cone, of course, to one light cone case, and there was something, for example, here. Oh, oh, yes. And we derived Bogomolny equations for such model. I don't remember the details because maybe I found, but I don't know where's my, I have other computer this file. Okay, Bogomolny equations are as follows, that we have such and so far and so far and so far. And now, what is the key idea? This case, general case, when the Bogomolny equations were derived, is the case when we have the model of couplet field U and V. The F1 and F2 are the sum functions, known functions, of the field variables U and V. And this is the case of Bogomolny equations. And now you can decouple these equations, and of course you can decouple the obtained Bogomolny decomposition, Bogomolny equations, and then the Bogomolny equations become Backlund transformation. And as you know, Backlund transformation is strictly connected to the integrability. Yes, because if you derive Bogomolny, Backlund transformation or Lax-pair, and so far you can say about the integrability of a given theoretical model. So we can,
like, yeah, if a theory is integrable, can you do this method?
I began
unclear.
analyzing this situation, the integrability from the viewpoint of still necessary conditions, but I have stopped this, but maybe I come back to in future.
Yeah, that's
Because
okay.
I had. Thank you very much for your
Yeah.
question. It was very inspiring, of course.
Thanks.
And Sokalski even, yes, Sokalski wanted to say to me, Lukasz, you have to deal with this. But he was very engaged in other problems, didactical, not only his private issues, and his life complicated in many ways. Then, but thank you very much. Yes.
Yeah, that's okay. Yeah, thank you.
Thank you.
Great. Maybe we can wrap it up there. So yeah, thank you again for the very interesting talk.
Thank you very much for making possible for delivering this talk, and for very inspiring and interesting questions and discussion.